In this video, I'm going to show you how to compute the determinant of a 3x3 matrix. But first of all, why do we even care about the determinant? Well, we care because, as we'll see in the future, the determinant is very useful. We can use it to find the area or volume spanned by a set of vectors. We can use it to solve systems of linear equations. We can use it to find the inverse of a matrix, and if you don't know what that is, you will soon. And we can also use it to understand linear transformations of objects in R2, R3, and even higher dimensional space. There really are tons of applications of the determinant, but for now we're going to focus only on the mechanical procedure. The applications will come later once we've mastered the procedure. So the way we compute a determinant is with this formula right here. And we'll talk about what this formula means in the context of this matrix, for example. In this formula, we've got some A's and we've got some M's. The A's refer to entries in the original matrix. A11 is just the first row, first column, so 1. A12 is first row, second column, so 2. And A13 is first row, third column, so 3. The M's, on the other hand, refer to determinants of matrices which are contained within the original matrix. And they're written with the letter M because they're also called minors. The subscript of each minor tells us which row and which column to remove from the original matrix. For example, the minor subscript 1,1 tells us to remove the first row and the first column from our original matrix. So we're just left with the bottom right portion, 0, 1, 5, 4. And that's what we want to take the determinant of. Likewise, the minor subscript 1, 2 tells us to remove the first row and the second column from our original matrix. So this corresponds to the determinant of the matrix 3, 1, 2, 4. Lastly, the minor subscript 1, 3 tells us to remove the first row and the third column of our original matrix. So we've just got the bottom left corner here, 3, 0, 2, 5, and we need to take the determinant of that. Before we proceed with the rest of our computation, notice that there's a minus on the second term here. There's no minus on the first nor the third terms, so it's easy to forget, but it's really important. If you forget the minus, then that'll throw off your computation, and you might get the wrong result at the end. Alright, so now that we understand how to use the formula, let's proceed with the rest of our computation. So we just need to calculate some 2x2 determinants. And that's not too bad. We just need to take the product of the diagonals and subtract. So here we've got 1 times product of 0 and 4, that's just 0, then minus product of 1 and 5, which is just 5, and then minus 2 times the determinant of this 2x2 matrix, which is just this product, 3 times 4, 12, minus the other diagonal product, 1 times 2, which is 2, and then plus our last term here, 3 times the determinant of this matrix, which is just 3 times 5, 15, minus 0 times 2, which is 0. And then we just simplify, so this is 1 times negative 5, and then minus 2 times 12 minus 2 is 10, and then plus 3 times 15, and that comes out to, this is negative 5, and then minus 20, and then plus 45. So negative 5 minus 20 is just negative 25, and then when we add 45, we get 45 minus 25, which is just 20. So that's our result. The determinant is just 20. Here's another example of computing the determinant, and we're going to move through this one a little bit more quickly because we've already done an example on the previous slide. So remember, our formula starts out with the first row, first column entry, that's 6. So let's write that down, 6, and then the corresponding minor is a 2x2 matrix obtained by removing that column and that row. So remove the first column, remove the first row, and you're left with the bottom right part of the matrix, which is 5, 3, -4, -1. Alright, so we've got our first term. Now in our second term, remember there's a minus here. So minus, then we put in the A12, first row, second column, is just 1. And then the minor there is obtained by removing that first row and the second column, which has the 1. And we've just got 0, 3, 6, -1. Alright, now the last term here, just plus the third term in the first row, so plus 2 here, plus 2 times the minor corresponding to this 2, so remove that first row, remove that third column, and you're just left with the bottom left section of the matrix, so 0, 5, 6, -4. Now that we've got it all set up, we can proceed with our computation. So this is 6 times this determinant, which is just 5 times -1, which is -5, and then minus 3 times -4, so minus -12, and these negatives will cancel out, so it'll just be plus 12. And then we have a minus 1 times this determinant, 0 times -1, just 0, then minus 3 times 6, minus 18. And then our last determinant is just 0 times -4, so 0, and then minus 5 times 6, so minus 30. And let's continue computing this. So this is 6 times -5 plus 12 is just 7, and then minus 1 times -18, and then plus 2 times -30. 6 times 7 is just 42, and then minus 1 times -18 is really just minus -18, which is same thing as plus 18, and then plus 2 times -30, that comes out to minus 60. And 42 plus 18 is just 60, and if we take away 60, then we just have 0. So that's the determinant of this matrix. Determinant is just 0. And we have a special name for matrices whose determinants are 0. We call them singular. So if you ever hear somebody say, oh, that matrix is a singular matrix, you know they're just saying that the determinant of the matrix is 0. In the future, we'll learn some other ways to compute the determinant. In all of these examples, we expanded along the top row, grabbing our coefficients as the entries from the first row. But in the future, we'll also learn how to compute the determinant by expanding along other rows or even columns. And we'll see that doing so can sometimes simplify the calculations.